Okay, so this is the question which was asked in GATE 2025. So this question belongs to chemical reaction engineering, and the question is given as the reaction A gives rise to products is taking place with the rate of reaction as minus Ra is equal to K into Ca cube. So it is an elementary reaction with third order reaction. So this reaction is carried in isothermal plug flow reactor at steady state, and the conversion is given at two axial points along the length of the reactor, that is at one location. It is the conversion is 0.3, and whereas in the second point the conversion is 0.6. So in the sense, conversion will be varied along the length of the reactor, whereas in CSTR conversion will be almost all uniform throughout the reactor because of huge mixing in the CSTR, but whereas here the concentration will progressively drops along the length of the reactor. In CSTR concentration quickly drops to the final value. So when we before entering into this PFR, we will see what is the performance equation for the PFR, plug flow reactor. So this is the flow into the reactor and flow out of the reactor. So the flow into the reactor, which is moving with a molar flow rate of Fa0, and initial concentration I am going to consider as Ca0, and the volume of the reactor is V, and length of the reactor is L. And the final concentration is Ca, and the final conversion of the reactants is XA. So if I write the material balance in this PFR reactor, so the rate of moles of reactant into the reactor, that is input, is equal to, so out of the reactor, that is out of the moles of reactants out of the reactor, plus disappearance plus accumulation. Since it is a continuous flow reactor, there won't be any accumulation of reactant inside the reactor, so accumulation is 0. So input is equal to output plus disappearance. So you will apply the molar balance by taking an elemental volume of PFR, and you will derive it. So I am not going to derive that expression. So finally I am going to write the expression for the PFR is tau is equal to, it is volume by volumetric flow rate, is equal to Ca0 integral 0 to XA dXA by minus Ra. So if we draw the curve, okay, how the rate of reaction varies along the length of the reactor, that is when you draw with respect to Ca versus 1 by minus Ra, so you will get a graph in a PFR. The rate of reaction will be varied like this. So along the concentration Ca to Ca0, if you find the area under the curve, that will give you volume of the reactor. So this is how usually will follow in solving this PFR. Similarly, whereas in CSTR there is an inflow of the reactants with Ca0, and final outflow of the reactants is Ca. And you will say same, you will write the material balance around this CSTR, that is input is equal to output plus disappearance. So here also in CSTR, since it is a continuous flow, there won't be any accumulation of the reactants. So the if you write the material balance, you will get the performance equation for the CSTR as tau is equal to Ca0 V into Ca0 by Fa0 is equal to volume by volumetric flow rate is equal to Ca0 minus Ca by minus Ra. So you are going to get this expression even if you plot a graph. If you plot a graph Ca versus 1 by minus Ra, and here the concentration is Ca to Ca0, So if you plot a since it is a CSTR, you are going to take area of the rectangle, so that will give you volume of a reactor. This area completely, it will give you volume of the reactor. So this is just basics what I want to introduce for PFR and CSTR. So now when it comes to this problem, so it is only data given is rate of reaction is given, and we need to find out what is the length ratio of L1 by L2 for the conversion 0.3 and 0.6. So for that what we will do is, so we are going to take this expression and we are going to derive that final L1 by L by 2 ratio. So here, so this expression, this tau, what I can write is, so since in the question it is given in terms of length of the reactor, so I am going to take this tau in terms of length by volume, so length by velocity. So length by velocity is equal to Ca naught integral 0 to xa dxa by minus Ra. So first what I am going to solve is for this PFR reactor. So I am going to take for this first condition up to length L1, what is the conversion? So conversion is 0.3. So for that I am going to derive first. So initially the conversion is 0, xa is equal to 0. So here I am going to take L by V. This is anyhow L by V is nothing but meter length is meter and velocity is meter per second, that is meter will get cancelled, you will get second only. So in terms of this tau time constant, I am going to write in terms of length by velocity. So L by, so since I am taking for up to L1, so L1 by V, so velocity is constant, so L1 by V is equal to Ca naught integral 0 to, so conversion is 0.3 dxa by, so here the rate of reaction is given as K into Ca cube, that is Ca cube into 1 minus Xa whole cube. So I am going to write the rate equation for this third order equation. So now I am going to rearrange this expression. So what I can get, L1 into K into Ca naught square divided by V is equal to integral 0 to 0.3 dxa by 1 minus Xa whole cube. So now I need to do the integration. So this is simple integration. You will do this 1 by 1 minus Xa whole cube and you will solve it, and finally you will get some value. So after this integration, so here I am going to get the value as 1.04, this integral term. So whatever this whole terms are there, that is K into Ca naught square by V, I am considering some variable as F, so L1 into F. Okay, so now this is for up to length L is equal to up to length L1, conversion is 0.3. So now I need to do the integration along the length from L1 to L2, varying the conversion from 0.3 to 0.6. So for that we will get the same expression only. So only change is L2 into K into Ca naught square divided by velocity. This is constant value. This is equal to, here the integral limits is going to change from 0.3 to 0.6 dxa by 1 minus Xa whole cube. Everything is same. So finally if you solve this integration, so I am going to get the value as 4.2. So this L2 into, so even this is a constant variable, I am considering as F, because all the remaining conditions are same in both the along the length of the reactor. So now I am going to divide these two equations. So I am going to get L1 by L2 is equal to 1.04 divided by 4.2. This is equal to, so here I am going to get approximately 0.24. So this is the final answer for this question. So in the sense, from here to here L1 is approximately 1 meter, and from here to here, that is L2 is approximately 4 meters. This is the dimensions of this plug flow reactor, 1 meter to 4 meter. So up to 1 meter length of the reactor, the conversion is 0.3. Again from 1 meter to 4 meters means 3 meters length of the reactor, it is almost all 0.6 meters. So like this we should solve for this kind of problem. Okay, for the same problem, for the same plug flow reactor, so at L1 conversion is 0.3 and at L2 conversion is 0.6. So now my rate of reaction is minus Ra is equal to it is K into Ca square instead of Ca cube, that is third order reaction. So I'm going to take rate of reaction as K into Ca square. So now you can check what is the ratio of L1 by L2. Is it same or different if you change the order of the reaction? So similarly you can do for K into Ca also. For first order reaction, what is the effect on L1 by L2? So these are the modifications you can do in the problem, and you can do it as a homework.